Hi there, we're in the lab with your mate JJ. Today is Learning the Art of Electronics Day. Today we're going to be learning the art of electronics. My silly job title for today is Note Taker. Today I'm the Note Taker. Of course, in the Learning the Art of Electronics videos, we're working through the lab course with the same name. We'll be doing a lab from the book today. We're still in the first chapter or the second chapter, depending how you want to count it. This is the lab for DC circuits, and DC circuits is the first topic in the book. We already worked our way through the notes section, that was 1N, and now we're in the process of working through the lab, which is 1L. What we'll be doing is popping over to the bench here and doing a simple experiment. We'll be looking at a voltage divider, and then we're going to model the voltage divider as a Thevenin equivalent circuit, and we're going to satisfy ourselves that the two circuits behave basically the same way. So that's the lab for today that we'll be doing. We'll take some notes in the notebook. Then I'll bring the notes from the notebook over to the computer. I'll type them all up, and the second part of this video will be reviewing the notes for this chapter. We won't finish this chapter today. There's more to do, but we will continue along the path. So let's pop over to the bench and let's do our experiment. All right, here we are on the bench. Now I'm just going to start our notes. Today is the 25th of November, 2025. I'm Australian, so I put the day first. We're working through Learning the Art of Electronics. This is 1L.3. So that's where we'll keep our notes. I'll show you the part of the book that we're working through. We're working here, we're doing the voltage divider. So we're going to construct the voltage divider showed in figure 1L5. We're going to apply Vn of 15 volts. It says use the DC voltages on the breadboard. Of course, I've got a 15 volt supply, so that's no problem. And then we're going to measure the open circuit output voltage. Then we're going to attach a 7.5k ohm load and see what happens. Then we're going to measure the short circuit current. And then from the short circuit current and the open circuit voltage, we can compute the equivalent, the Thevenin equivalent. Then we're going to build the Thevenin equivalent using the variable DC supply. And then we're going to check that its open circuit voltage and short circuit current match those of the circuit that it models. Then we'll attach the 7.5k load again, just as you did with the original divider, to see if it behaves identically. Okay, and here it is, the humble voltage divider in figure 1L5. So we're going to have two 15k resistors, and that's it. So let me put the circuit together quickly. All right, so that's done. I've made the circuit that we'll be using today. The power comes in over here. There's two 15k resistors forming a voltage divider. The output voltage is here and here. It'll be half the voltage will show here, and this is ground, common ground for everything. So, let me just tidy up quickly. All right, well, we're going to need power. So let me show you power. There's power. There we go. So I'm just going to throw the power on. There we go. And we'll just use the top one. And we'll be taking 15 volts, wasn't it? V set 15. All right. And then that just comes out here and goes into here and then goes into here. So that's our circuit power all wired in. It's not turned on yet. Now, what are we going to be measuring? I think the first thing we're doing is the short circuit current, isn't it? Construct the voltage divider shown. Apply 15 volts. Measure the open circuit voltage. All right. So let's put our meter in voltage mode, and we'll get some banana cable to DuPont female. That's what we'll use. So we're going to test the open circuit voltage. We've got common and positive, and then we're going to put that on positive and that on negative, and that is the open circuit voltage. So let's throw the power supply on. It's delivering 15 volts. It's not drawing any current, and the open circuit, so VOS for short circuit equals 7.52 volts. All right, and then I believe the next thing we're doing is we're going to attach a 7k load and see what happens. All right, so here's our resistor. Let's just get it recalibrated. And if we want 7k, 7.5k. So 7k, 4, 5, 6, 7, 4k plus 3k, that's 7k. And then 200 plus 300 is 500. So that should be, that should be 7.5 ohms. So 7.5k ohms. Of course, we can put our meter here into ohms range, and then we'll put in here, and we'll just see that we've got that right. What are we dealing with? 7.49, close enough. So we've got our load resistor. So let's put our load onto the circuit. So we're going to need some more banana cables to DuPont female. So I've got that here. So this is, of course, it doesn't really matter, negative and positive, the thing. So we'll turn the power off while we're installing everything. And we're just going to put the, might as well keep the colors the same, no reason not to. All right, so now we've got a I'm a little bit annoyed. I didn't think to put in the jumpers. Anyway, it doesn't matter for this part of the measurement. So let's just throw the power back on. All right, and okay. So the voltage across the load has gone down. So we'll call it V with load equals 3.761. Okay. And then the next thing that we're going to do is measure the short circuit current. Now in this case, we'll be able to do that. The short circuit current is no problem. So let's turn the power off. And we'll just put this away because we're done with this. And the power we still need. The resistor will come back to. All right. And we're going to measure the short circuit current, which means we can just take our voltmeter and put it into current measuring mode. Let's measure milliamps. And we'll plug him in there. All right, now we're going to turn our circuit on. And we'll be measuring the short circuit current, which is 1 milliamp. So V short circuit, sorry, that's not V. I short circuit equals 1 milliamp. Very good. All right. All right, so what are the other measurements we need to do? Now we need to build the Thevenin equivalent circuit. All right. So the Thevenin equivalent circuit will just be this resistor, which is the 7.5 kilo ohm resistor, in conjunction with the 7.5 volt 7.5 volt power. So just over here, I'll put the voltage on 7.5. All right. And we'll use our jumpers. Start some jumper power here. So that's positive and that's negative. Now what we're going to do is run the positive lead into the resistor, and then we're going to check the voltage. Oh shit, still in milliamp meters. Put it back on voltmeters. All right. So the V open circuit equals 7.51 volts. And how are we going to load that? I guess we'll just add a resistor. Is that right? So let's make another 7.5K resistor. And we'll just wire it in. No, that's not right. I'm going to take a break. All right, so this has just got a bit to be a bit of a mess. So let's just clear up. All right, now we're going to have let's get this stuff out of the way. All right, so we've got the positive voltage coming into one of our resistors, and then we've got a voltage coming out of that resistor and into this resistor, which is going to be connected to ground, which is here. And then we've got a we've got a voltmeter here, and we want to see the voltage across the load. So we've got one positive, which can just go here. That's fine. And then this one, which can go here. And we're measuring voltage, and we've got the V with load equals 3.758 volts. And then the short circuit current. All right. So let's take this out, and we'll put him in current mode, and we'll measure the short circuit current. So send the current in here, and then out here. Is that right? Oh shit, that's not the short circuit current. That's the load current. All right, we'll turn him off. The short circuit current, we don't need the load resistor for, so we're done with the load resistor. And to get the short circuit current of the thing, we just need to connect these two here, and then we turn that on, and the short circuit current is 1 milliamp. Spoiler, it's the same. It's supposed to be the same, and it is. So this is the voltage divider, and this is Thevenin model. So our voltage divider gave us these readings. The Thevenin model gave us those readings. They're the same. The why have I put S there? It's not OS, it's OC. Open circuit. Open circuit. So the open circuit voltage, which is the Thevenin voltage, was 7.52 volts. With load, it was half that. The short circuit current was 1 milliamp. For the Thevenin model, the same. So that's the end of the experiment for today. What we'll be doing now is going over to the computer, writing up the notes, running through the notes for this chapter, and then we'll be done. So let's pop over to the computer to finish up. Right, so here we are on the computer. I got the notes written up, so let's go and have a look at that. We'll just do the revision, and then we'll go through the results of our lab exercise from today. So we're going to go to the ITL wiki. This is inthelabwithjj.com/wiki, and we'll be working through learning the art of electronics. And we'll be going through the second edition of the book. And we're up to lab DC Circuits Lab. So let's open that up. All right, now we'll just do some quick revision. You've seen this already. We covered this last week, except for the new material that we'll get to at the bottom. So as they say, the point of this lab is to get used to the breadboard and the multimeters. So it's just a hands-on lab. We're not expected to find any of the findings particularly surprising, specifically Ohm's law, which is of course V equals IR. So actually, I'm just going to go grab a coffee. I'll be right back. All right, I've got my coffee. So on we go. It says here to build your breadboard on the breadboard, your circuit on the breadboard and not in the air. Of course, we did one better because we built our circuit on the proto board. So I've got these great electro cookie circuit boards that I use. So we actually didn't use the breadboard. Well, we did actually build our second circuit in the air, didn't we? Because it was just a resistor and a voltage source. So we just needed a few big banana cables for that. Anyway. So there's a note here that voltages are measured between points, whereas currents are measured through a point. Analog meters are known as VOM, short for volt ohm milliammeter, and digital meters are known as DVM, short for digital voltmeter. They're also, of course, known as DMM, which is digital multimeter. So to measure a current, a DVM runs the input through a small valued resistor and measures the voltage drop across the resistor. The small voltage that the DVM drops when measuring current is called the burden voltage. You should be skeptical when measuring components in circuit. It's best to disconnect at least one end of a resistor before taking a measurement. Now, something that I haven't been doing here that I've started doing today is indicating when values are measurements from a lab. These were readings that I took in the lab, but it's not clear what was a measurement and what was calculated or an input. So I'm not sure if I'm going to go back and fix this up, but going forward we'll be using the new scheme. So this is where we're up to. This is where we started today. Oh, no, that's not right, actually. This is where we started today. So there's a few notes here that I made following on from last week. So we'll learn about capacitance in Lab 2. Our DVM can use its current source, which it uses for measuring resistance, to measure capacitance as well. The current that says current course. That's supposed to say current source. What are we going to do? Give me a sec, I'll be back.
All right, I'm back and I fixed that. So it says the current source changes the capacitance. Sorry, not changes. The current source charges the capacitance under test, then samples the voltage to infer the capacitance. This is non-trivial to do, but sophisticated software and electronics in your DVM can do it. We will learn later how to infer capacitance from the frequency of an operation. If we build an oscillator set by an RC time constant and use a known R is for resistance and C is for capacitance, the frequency/period of the oscillation indicates the value of the capacitor C. If you measure one capacitor and then another, if the period doubles, for example, then the value of the new capacitor is twice the first. So that was just chatting about capacitance, and we're also going to have a chat about the beta of a transistor. Soon we will begin to learn about bipolar junction transistors, which is BJTs. We'll also be learning about MOSFETs and JFETs and other types of transistors. A transistor's beta, it's the Greek letter beta. I believe that's lowercase beta, isn't it? Yeah, it is. Uppercase beta just looks like a Latin B. Anyway, a transistor's beta characterizes its current gain, the ratio of the current out, which is the current through the collector, to the current in, which is the current through the base. Beta is a slippery characteristic because it varies a lot with temperature, current, and from one transistor to another. Fancy DVMs won't include a beta measurement, probably because it's not reliable. And then this is the voltage divider. So in this lab, we construct the circuit in figure 1L5. So this is 1L5. And that's the circuit that we made today on the breadboard, or on the circuit board. So we apply 15 volts in, and then we measure the open circuit voltage. Then we attach a 7.5K load and see what happens. Now, that's not very clear, is it? So the two things that I guessed it wants to know are, oh, I didn't check the current, did I? Just check the voltage. Anyway, then we measure the short circuit current, which is not with the load. So I measured the voltage open circuit and the voltage with load, and I measured the short circuit current, but I didn't measure the current with load. Perhaps I should have. It wasn't clear. It didn't say to. It just said see what happens. Anyway, I'm out of time now, so we're not going to take that reading. So it's 8:30 on Tuesday night. I've got like 2 or 3 hours to get this video out. So I'm rushing through to the end. And as I said, I'd be doing my measurements, and the way that I'm going to indicate measured values is I'm going to put them in blue like this. So this blue indicates that we've measured a value. It's the result of our experiment. So as you would know, the first circuit that we did was the voltage divider, and then the second circuit that we did was the Thevenin model. So the voltage divider gave us these characteristics. We calculated them. Sorry, we measured them. And then we could use these values. The Thevenin voltage just straight up is the open circuit voltage. So that's just 7.5 volts as measured. And the Thevenin resistance is just the Thevenin voltage divided by the short circuit current, which in this case is 7.5 volts divided by 1 milliamp, which is 0.01 amps, which equals 7,500 ohms, which is 7.5 kilo ohms. And then we build the Thevenin equivalent circuit, and we check its open circuit voltage matches the first circuit, and it does. And then that its short circuit current matches the first circuit, and it does. And of course, the voltage with load also agrees. We took that basically by putting the 7.5 K load in parallel with the bottom half of the voltage divider. We get the 7.5 in parallel with 7.5, which halves the voltage, giving us 3.75 volts. So that's it. That's everything we've done today. There's more to come in this chapter. We'll continue working on that next week. The little innovation today is the colors for the measurements that we take when we're doing labs, so that in the future that'll be clear what we've added and what came from the books or calculations. So yeah, I'll throw over the farewell cam. We'll wrap up.
Let's wrap. So we continue to learn about voltage dividers, and we continue to learn about Thevenin equivalent circuits. So today, I think we just reinforced something that we'd been learning already in the first in the notes for the first part of the course. So that's everything for today. We'll continue next week. This is the end of the video. Hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.